So let's get started. It's a real pleasure to be here. This is a topic of great enthusiasm and interest by many members of our community. So I'm delighted to be able to share some of the thoughts that we've been having in this regard. Historically, the word AI, we keep hearing it more and more since the last decade, but, AI is a very broad term that applies even to, rule-based, systems or gaming systems, for example, chess playing systems, etc. But what has happened, especially in the past few decades, is that machine learning, which is a branch within AI, has really shown tremendous value, where you're sort of getting rid of explicit logic, like sort of saying, if this, do that kind of statements, as had been common in other sort of rule-based approaches, getting rid of those as much as possible. And within machine learning, you have deep learning, especially sort of taking off in the past decade, where it's sort of a similar paradigm, but you're doing even less hand coding and extracting features from, let's say, the images and letting the system to pretty much, providing it with a lot of raw data and letting it figure out a lot of things. So again, to sort of try to understand that a little bit better, in conventional paradigms, what you have is data provided to an algorithm, for example, that you're having. Let's say you want to delineate a tumor in an automated way, and you have an algorithm that, for example, says if the intensity changes significantly, that probably means you're at the edge of a tumor, and then therefore you delineate what you have. But the sort of the new paradigm that is been very exciting in machine learning is that you don't give it the algorithm, you actually provide it with the data and some kind of output, and the output is, for example, is a training set. It could be the delineations by experts like yourselves, nuclear medicine and radiology experts. And the system sort of based on the data and the output, what the truth is, what the output is supposed to look like, actually extracts the algorithm, right? So again, machine learning is within AI, and within machine learning, you have deep learning where you do even less and less handcrafted features, and you just give it the raw, for example, images and let it figure things out based on, for example, training data sets. So, AI is a very hot topic. We just had this special AI issue in pet clinics come out, so please check it out. It's on AI and pet imaging. Part 1 has 14 fantastic articles, more on the technical side, historical aspects, history of AI. For example, the first article's on a brief history of AI and how to avoid the next winter, because we're in the 3rd summer of AI. We've had 2 winters where things were looking good and then they went downhill, 2nd winter, and now we're in the 3rd summer. Hopefully there won't be another winter. And the question is, what have we learned from the past couple of winters to avoid a next one? But clearly, as I'm sure you couldn't have avoided, AI is a very hot topic. And in the second issue, which is upcoming in the part 2, we're going to have fantastic articles on use of AI in specific diseases, for example, prostate, lymphoma, rare diseases, et cetera, et cetera, et cetera. And a number of articles on, various aspects. So please check this out. So I was tasked to put together a task force, AI task force for the Society of Nuclear Medicine and Molecular Imaging, and we have around 20 fantastic scientists and physicians and statisticians, from different walks of life and different backgrounds that have joined this task force. And we've been having meetings and gatherings for the past year. Specifically, we've had 3 teams. Team 1 led by Dr. Babak Saburi, team number 2 led by Dr. Tyler Bradshaw, and team number 3 led by Dr. Abhinav Jha, where we've been talking about the AI ecosystem, what it takes for AI systems to really take off in the clinic, what is the ecosystem, what are the opportunities and challenges. And then we've had for team number 2 best practices on how to actually derive and arrive at AI algorithms that are robust and meaningful and reliable, and finally, how to actually validate them for ultimate translation to clinical tasks. So I'm going to talk about these discoveries that we've had and discussions that we've had in these teams. So again, team one, focusing on opportunities and challenges towards trustworthy AI. So the way we've thought about it, I want to pick your brains about this and to see if you sort of see it the way we're seeing it. We sort of think of nuclear medicine as a cycle where you start with the patient and the provider, and you go all the way to the image, and you come back again to the patient. So you start with the patient who is going to be imaged, right? So you're going to have appropriate radiopharmaceuticals and radiochemistry, appropriate instrumentation, image acquisition, image reconstruction, post-reconstruction, and image enhancement to arrive at an image for the patient. And then you're going to do something with that image, right? To go all the way back to the patient and the provider and do an iteration, or to make this, to make clinical decisions. So this could be by analyzing the image, for example, segmenting the tumors, measuring the molecular tumor volume, the metabolic tumor volume in the case of FTG, for example, and other ones, doing discovery, doing diagnostics detection, enhanced reporting and informatics, and finally arriving at decision support and making recommendations, right? So, and the point I want to make is that AI can enter in every single step within this cycle. And the special AI issue of Pet Clinics really has articles on all of these, pretty much all of these, right? So how are we going to use AI for better radiopharmaceutical design, for better radiochemistry, for all these steps of creating an image and all these steps of analyzing the image and coming back and making recommendations and clinical decision making. So AI enters throughout, so from patient to image and from image to patient. And just to provide you with one example, we believe strongly that AI is going to have tremendous impact in radiopharmaceutical therapy, which of course is a very hot area, as you know very well. And so this could be on, optimizing image acquisition, reconstruction, denoising of the images, allowing us to segment the tumors. For example, if we want to do, let's say, dosimetry, personalized radiopharmaceutical therapy, we want to do dosimetry. So you need to register, images of the patients over multiple cycles of radiopharmaceutical therapy, segment the tumors and the normal organs, understand the uptake patterns over time, computing, the time integrated activity maps to see how much dose is being delivered to these organs at risk and to the tumors, and to find the right balance, right? So you don't want to inject too little because you're not going to treat, and you don't want to inject too much because you're going to have toxicity in normal organs, but finding the right balance. Because presently, dosimetry is not routinely used at all, and we believe that personalizing and computing dosimetry for every patient allows us to do even better in these exciting trends that we're seeing in radiopharmaceutical therapy. So how are we going to actualize opportunities that AI gives us? Let's say we want to automate dosimetry calculations on our patients, right? Or we want to calculate metabolic tumor volume in every single lymphoma patient, because we know MTV is highly predictive of outcome, but it's just not being computed in the clinic because it's too time consuming to delineate all tumors and, let's say, compute total metabolic tumor volume, TMTV, in DLBCL patients, right? So how are we going to actually do that in a reliable, trustworthy manner that you trust, that our patients trust, right? So there's a need for a concerted effort to promote applications of AI technology, engage in academic, industry, variety of other funding resources, right? I mean, we're trying not to be naive. Like, as a scientist myself, I get excited by particular AI algorithms, but I just know there's a long distance from me being excited about something and it actually being used routinely in the clinic. So how are we going to enable that to happen, right? And how are we going to do that while protecting our patients and our society? So again, you're trying to, let's say, design an AI system that is going to interact with the patients and the nuclear medicine providers, how are we going to make this a trustworthy AI environment? And what ecosystem are we going to need? Well, obviously, we need the participation of the AI industry, the health systems. We need some kind of an orchestration platform. You know, how these interact with the local PACS, with the nuclear medicine imaging archives. How are these AI algorithms and methods going to be approved? How are they going to be compensated? What are some legal aspects of it? And also some ethical aspects of it, which we're working on as we speak. And, you know, AI system evaluation. And, you know, how are we going to harmonize all these different elements that contribute to AI algorithms to take off in routine clinical practice. So the challenge of AI trustworthiness is actually great. You know, and it pretty much, if you want to define what is it, or measure what is the level of trustworthiness of a tool, is basically the willingness of you, the physicians, and the patients to depend on a specific AI tool in a risky situation, right? And so this consists of trustworthiness of the AI system itself, but also all the people and processes that are part of the system's life cycle, so the AI ecosystem. So we've identified 12 dimensions and aspects that enable and contribute to AI trustworthiness. You know, one of the primary ones is human agency. At the end of the day, the AI systems have to be at the service of humans. At the end of the day, even if you have an autonomous or so-called autonomous system, at the end of the day, it has to be at the service of humans and contribute to tasks that are overseen and designed and understood by humans. You know, so oversight is clearly important. Safety, security, change control. Let's say you have an algorithm that works really well, but suddenly there's a minor, you know, update or a new version. But since many AI algorithms have in the past been blind and it's sort of a black box, and it's very they have been complicated, and it's been very difficult to understand what exactly it is that they're doing. What if suddenly the new update doesn't work as well? Or what if suddenly you have a different kind of patient of a different ethnicity, or a patient that is highly obese that has not been in the training set, and suddenly the algorithm doesn't work? So issues of diversity and bias awareness, right? And, you know, can you understand what is actually going on in these algorithms? So issues of transparency, explainability, fairness, and things like that, and privacy. So again, these 12 elements combined with the appropriate ecosystem, we believe will contribute to the to trustworthy AI algorithms. So it's AI algorithms. So it's a road ahead. Already, of course, AI systems are increasingly being approved, and in different fields, you know, outside of nuclear medicine and increasingly within nuclear medicine. And we believe that there is a need for a really concerted effort for the amazing potentials of AI to enter the picture. So so that was sort of what team one was discussing. And team number two, just to really understand some of the challenges with AI and some of the best practices. Let's move on to team number two and the discussions we've been having there on best practices for algorithm development. Okay, so one of the, you know, AI has a lot of pitfalls. There's been a lot of exaggerated claims in the literature. You know, many papers sort of saying, oh, this is the best thing that's happened ever, right? And so I was looking at this university news piece from some university somewhere, and you know, somebody was saying, you know, I was looking at mild cognitive impairment patients and predicting outcome of them, and I was 99.99%, you know, having accuracy. And the problem was this person was only using a training data set, no separate validation, and basically just fitting a lot of parameters in his data set and arriving at perfect results, whereas it was not independently validated. So a lot of exaggerated claims. Poor reproducibility. You publish something, other people cannot reproduce it. Poor generalizability. You develop something that works for your hospital and it won't work for another hospital. And biases. You know, you've been hearing about the fact that AI systems can be racist and sexist, for example. If the training data set that you have is limited to a particular ethnicity or gender, you're going to have issues. And black box problems, not knowing exactly what's going on inside. And so just to show you one example, imagine you have two different patient populations, let's say cancer patients and healthy patients, right? And imagine the y-axis is, let's say, the SUV value in a PET scan, and the x-axis is like the tumor volume. So you're plotting these, and an AI system is supposed to distinguish between these two sets. But since AI systems have a lot of parameters, they could actually fit the noise here, and they could actually do a perfect, absolutely perfect separation between the. So look at the green curve, let's say of a naive AI system that is basically, separating really, really, really well between these two patient populations, 100% accuracy. But really what it's doing is fitting noise. And the black curve is probably going to be a better, more generalizable system, but here you're overfitting. So it's going to work perfectly here for this particular patient's data set, and it's not going to work well at all in a different data set. So you know, the issues of overfitting of your data, how do you avoid that? So the good news is there's definitely solutions to this, and increasingly AI networks are aware of this, and AI developers are aware of this, and our best practices really emphasize that. Just to show you a prime example in the era of COVID-19, where there's been thousands of AI algorithms developed for different tasks related to COVID-19. There have been really exaggerated claims sometimes. Somebody saying this toolkit can easily be deployed worldwide to other hospitals, right? A very, very strong statement, which is likely not true. So there was a study that came out. Basically, they studied over 2,000 publications on using AI for COVID-19, narrowing that down to about 415 after initial screening, further quality screening to another 62, highest quality studies within these 2,000. And then they say, our review finds that none of the models identified are of potential clinical use due to methodological flaws and or underlying biases. So there are many different issues, right? So some studies, for example, they had mixed up training and testing sets. So they were developing the algorithm based on a set, but some of the patients in the training set were also used for validation, which is a bad problem. You shouldn't be using patients in both training and in the testing set. Some had actually, for example, had done for normal non-COVID, they had used children, whereas for COVID-19, they had used adults, right? And because children, are less likely to have COVID-19, really what the algorithm is probably doing is separating children from adults, not non-COVID from COVID. Or people had used Frankenstein, so-called Frankenstein data sets, where they take some data set, they add other things to it. It's really not clear what this data set exactly is, so you cannot reproduce the work. So different kinds of problems, right? So this was a highly publicized publication, sort of grounding a lot of AI researchers saying, hey, we got to do better. So we made a number of recommendations. And looking at study design, how to design a study, how to collect data, how to label the data, how to develop actual models, how to train models, how to test models, how to report your actual findings in a publication, and how to finally do evaluation. Once you've developed a model, publish it, how do you actually evaluate it, for example? So I won't go through too many details. We've made very specific recommendations. This is going to be published very soon, hopefully. And for example, in study design, we've distinguished between AI method development versus evaluation, right? So a number of recommendations. So one of the obvious ones, or so supposedly obvious ones, when you publish something, make the code and the models accessible, so other people can actually use what you did and confirm what you did, so you're actually moving forward, right? Use of external data sets is encouraged in development studies and is a requirement in evaluation studies, right? Making clinical claims is not a part of development studies, but it has to be a part of evaluation studies, et cetera, right? So looking at data collection, we have to anticipate biases. We have to understand that your model is as good as your data. So if your data is only on, let's say Caucasian males, you're very likely going to have biases when you have other ethnicities and genders enter the picture, right? So being very aware of that issue. Label quality should be justified by application and study type. So when you're labeling the data, let's say you're providing reference truth delineations of tumors, so that the machines learn from human experts how to delineate tumors and therefore how to compute the volume of a tumor, right? So there's different qualities. I mean, you could do approximate labels, single labeler. Often we're here, multiple labelers is even better. And finally, some kind of ground truth, like having biopsy confirmation, post-mortem surgical, and doing phantom studies. So there's different levels of, or qualities of annotation, and we have to be very aware of them. Model development, sometimes you have extremely complex models, but you really should try to compare those to simpler models because it may be unnecessary. So Occam's razor, essentially. How to train your data sets. It's important to have, obviously, separation between training and testing. And within your training set, where you're developing your model, there's a so-called validation step where you're trying to avoid those overfitting of noise issues that I was mentioning to you before. So some technical aspects that I won't go through. Finally, or not finally, but when you're doing model testing, you got to have appropriate metrics that you're going to evaluate, but also look at what the output looks like. Don't just evaluate metrics. Look at the data, play with the data, and try to test performances in external data sets because there may be shifts. If you're only testing in a single center, you may not be seeing shifts in the data that may happen when you're moving between different hospitals and centers. Reporting, there are guidelines on how best to report AI findings. So it's very important to report very transparently and thoroughly so others can reproduce your work. And finally, once you have an AI algorithm published, established, how are you going to evaluate it for translation to clinical practice? And that's a whole different topic. And that brings us to team number 3, which I will talk about. So the summary here for team number 2 finding on best practices for algorithm development was AI really has many promising applications. The pitfalls are real but manageable. And hopefully in fact, certainly these best practices can help accelerate clinical translation and to build trust. So that was team number 2. Team number 3 is about best practices. Once you have an algorithm, how are you going to truly evaluate it for routine clinical usage, right? So moving beyond, deriving and publishing and arriving at some AI algorithm, and there are, again, thousands of them, for example, in COVID-19 cases. How are you going to take these and translate them? So for clinical translation, you need rigorous evaluation, right? And we know that. Evaluation may require special criteria. Obviously, these algorithms are learning from the training data. So the performance really depends on the training data. So if you have a limited data set, your algorithms cannot do magic, and it will be very likely limited. And output can be really unpredictable and often has been in the past not interpretable. So we need to evaluate AI methods, identify cases of failure increasingly. So one of the good things that you see in publications, and it's a sign of maturity by scientists, is that, sure, they report my algorithm works really well, but they also show examples where their algorithm fails. It's a sign of maturity to report that. And so identifying cases of failure, reporting that, and you really have to focus on specific tasks. The question is, how well does my algorithm perform on what task, right? So you need to assess generalizability. You may have developed an algorithm that works really well for your center and suddenly it doesn't work for another center. So there have been a lot of generalizability issues for AI algorithms in the past. Something that works really well today may not work 5 years later, where your patient population may have drifted, right? And so post-deployment settings, evaluation in that context is going to be very important. And the claim, so we're emphasizing in our task force that when there's a publication, when there's an evaluation, there should be a claim associated with that. There should be an accompanying claim, right? Consisting of the following components. You should really define what the task is. For example, task could be classification of disease. It could be quantification of, let's say, tumor volume. It could be a combination of the two, stating what the patient population that was used for training was, right? The imaging process, the imaging systems, single multi-center, for example, nature of it, understanding how the tasks were actually evaluated, like was it a human observers that evaluated the detection, or was it some kind of a computer that evaluated the detection, performance, quantification, similar things, and what kind of figures of merit were used to evaluate the performance of, let's say, human observers, right, on the performance of the AI system. So increasing evidence of generalizability will be achieved as you move from the left to the right. From the left, you have no external validation, single reader, single scanner, specific population, which is a lot of the publications that we're getting in the literature now. But as you move to the right, where you start to have external validations, right, which could be, let's say, one other center, or even within your center, but a separate data set that you have not looked at all, right? So you've developed your algorithm, you have even evaluated, but now you get yet another set in order to evaluate your algorithm. But ideally, it should be from multiple centers, multiple readers, multiple scanners, a increasingly diverse population. And so the more you move to the right, you're going to have higher confidence for application to general populations, right? And so we think of evaluation framework as in this pyramid. Initially, you may have a publication. Many of the publications might be here, just a proof of concept evaluation. Simply saying, my AI algorithm has promise, right? And let's think of an example of segmentation. So in the case of segmentation, you may do a very simple evaluation using so-called DICE scores. DICE scores are measures of how good segmentations are, basically how well your segmentation overlaps with an expert segmentation. But then you start moving beyond just saying, oh, this is promising, but actually doing more technical evaluations. So in this case, we want to, for example, measure the metabolic tumor volume. How well does it perform, not on the DICE score, but how well does it perform on actually measuring metabolic tumor volume? So that's a technical evaluation. You move up, now you start making clinical claims. We want MTV for something. MTV on its own is not useful. We want MTV for a purpose, for example, to prognosticate patient response. So there, you're now making claims on efficacy, on making clinical decisions. That does my MTV automatically generated metabolic tumor volume for DLBCL patients? Does that anticipate and prognosticate patient response? And finally, once you have a system, you do post-deployment, clinically effective maintenance related issues. Does it work with different populations over time? So just to re-emphasize that. So class one would be, again, class one is at the bottom here, just proof of concept, right? So how good is this segmentation using something like a DICE score? So the claim would be something like, my PET segmentation method evaluated on patients with locally advanced lung cancer acquired in a single scanner with single reader evaluation yielded a DICE score of whatever, right? So being very upfront, being very transparent when we're making publications and making claims about how well my algorithm works, so that we're not making exaggerated claims and we're all working together as a community to be well grounded and to move towards generalizable, trustworthy AI algorithms. Technical evaluation, moving up the pyramid, is going to be like, okay, let's look at MTV. How well does this reproduce MTV? How accurate is it? How repeatable is it? How reproducible is the MTV measurements, right? So finally, clinical evaluation. Does the MTV that I have derived using my fully automated AI system make predict outcome well, allowing us to make some therapeutic decisions. So the claim on the previous one would have been, my method yielded MTV values with a bias of whatever, evaluated using certain phantoms on a single scanner or multiple scanners or what have you. Here, however, it would be early changes in MTV measured from images with an AI-based segmentation method yielded an increase in area under curve performance with a change of whatever in predicting overall survival in patients, right? So being more and more specific, more transparent about what the exact claim is. And finally, you're looking at post-deployment. And here's a plot of the scope of the monitoring study, looking at just observation, post-deployment observation, single center, multi-center, and the goal being just to watch, to validate, and to innovate, and to take, what the algorithms that are being used right now in the field, and to sort of make sure they're maintained properly, and in fact, they're upgraded to accommodate new populations and new challenging scenarios. Okay, so I'm wrapping up here. Basically, there are elements of study design for each class of evaluation. So you need to determine the study type. What are you doing? Are you doing some digital phantoms, some real physical phantoms, or actual patient studies? How are you collecting the data? Are they representative? Are you having external validation? Define your reference standard. Are you doing, for example, multi-reader studies, which is the kind of recommendation we're making? And finally, figures of merit that you're using to actually evaluate. Are you just doing, proof of concept evaluation, technical, clinical evaluation, etc.? So we're gonna make a reliance guideline, and hopefully this publication is gonna come out soon. So reliance here stands for recommendations for evaluation of AI for nuclear medicine, on how to design each of these. Okay, so in summary, AI in nuclear medicine presents immense and exciting opportunities. There's rigorous evaluation that's needed for clinical translation. And I think hopefully the good news I'm conveying to you is that on our end, scientists are starting to see the concerns, right? The concerns and the issues with AI algorithms being in this black box, often not being interpretable, being overly complicated, not being non-generalizable, sometimes not even useful, and sort of being better grounded, learning from our failings of the past, and sort of moving towards trustworthy AI algorithms that you and the patients and the entire ecosystem is going to rely on. And again, the intention of the guidelines is going to strengthen the trust and accelerate clinical translation. I just want to make some remarks, which is not exactly related to what I've been talking about so far, but I think these are sort of anticipations of where we are in the future. AI will replace some mundane activities by clinicians, like low-hanging fruits, enabling you to spend more time with patients. I think that's one of the benefits of AI that's going to happen. And also it will do certain things that you don't have the time to do, such as very mundane and labor-intensive tasks, like, again, delineations of edges of the tumors throughout the body and computing the total tumor burden in the patient and providing further value to you to make better decisions and readings. It will not replace clinicians, right? But those that do not embrace it may be replaced by those that do. AI is here. I don't think it's going to be going away. And even though sometimes there have been significant exaggerated claims and expectations, but I think the community is recognizing the limitations, and hopefully we'll be working together to address the challenges. And in fact, radiology itself, as it did not exist prior to the radiological technical revolution of the 20th century, it was accidentally discovered, really, when you think about it, radiology. So I think we need to also embrace and welcome new technological revolution. It's in our DNA in the field of radiology to be open to new technologies and new discoveries. And I think in the case of AI too, it's happening and will be happening. I really want to acknowledge members of the AI task force, the various team members, lots and lots of fantastic meetings and gatherings. yes, and thank you for listening to these to this presentation, and open to any comments or questions. Thank you.